Why do AI systems need to explain themselves? In high-stakes settings, a prediction alone is not enough because people need reasons they can understand and evaluate. This video explores why explainability matters, how major explanation methods differ, how robust they are in practice, and how they can be applied. Explainability in AI is the ability of a system to provide understandable and interpretable justifications for its predictions or decisions. It matters because trust, accountability, and adoption depend on it. This becomes especially important in areas such as healthcare, finance, and law enforcement. Explainable AI helps systems reveal how decisions are made and why they should be accepted. That transparency supports ethical and regulatory expectations. In high-stakes domains, explainability is linked to trust, accountability, and compliance, rather than being a nice extra feature. Explainability also helps identify responsibility for decisions, which supports ethical and lawful use. When users and stakeholders understand an AI decision, they are more likely to trust the system behind it. A healthcare provider, for example, can better trust a tool that explains a diagnosis. Explainability is also tied to regulation. The material highlights the General Data Protection Regulation, the European Union AI Act, and financial regulations in banking and credit. These frameworks emphasize transparency, accountability, fairness, and interpretability in decisions that affect people. 3 key ideas shape explainable AI. Transparency is openness about how a system works. Interpretability is the ability to understand how a specific decision was made. Justification is the rationale for a decision in a form that fits domain-specific standards. The level of explanation also changes by context, with healthcare needing more transparency than recommendation systems. Model-specific explanations are tailored to the internal structure of a particular model. Decision trees and feature importance in linear regression are examples. Their strength is high transparency and detailed insight into decision-making. Their weakness is limited use with complex models, such as neural networks. Post-hoc explanations are created after training, often for black box models. The material names SHAP and LIME as major techniques. Their strengths are broad applicability and attention to individual predictions. Their weaknesses are computational cost and the risk of oversimplifying true model behavior. Intrinsic explainability means the model is interpretable by design. Rule-based systems and logistic regression are given as examples. These methods are easy to understand and communicate because explanation is built in. The trade-off is that simplicity can reduce accuracy in complex tasks. Across the 3 approaches, the pattern is clear. Model-specific and intrinsic methods offer strong transparency, but struggle with complexity or scale. Post-hoc methods are flexible enough for black box systems, yet they may cost more to run and may not fully capture the real decision process. LIME generates a local surrogate model to approximate the decision boundary around one specific instance. That makes it useful for explaining individual predictions in a user-friendly way. But for large datasets, it can be computationally intensive, and similar inputs may receive inconsistent explanations. SHAP assigns contribution values to features for a prediction and can support both local and global understanding of model behavior. The material describes SHAP as consistent and theoretically sound. Its main weaknesses are high computational expense and the need for careful implementation and interpretation. The material also compares model-specific and model-agnostic methods directly. Model-specific methods fit interpretable models such as decision trees and linear regression, giving high transparency. Model-agnostic methods can work with any model, including black box systems, but add overhead and may oversimplify. In healthcare, explainability supports tasks such as disease diagnosis and medical imaging. SHAP can identify important factors such as age, symptoms, test results, or key image regions. This helps build clinician trust. However, explanations may be less robust in rare cases, subtle variations, or outliers. In finance, explanation methods are used for credit risk prediction, loan approval, and fraud detection. SHAP can highlight important features such as income, credit score, credit history, transaction amount, or location. LIME can explain individual outcomes, but its results may vary for similar cases. Rule-based approaches are transparent and easier to audit for fairness. Their limitation is lower adaptability to changing patterns and reduced predictive accuracy. Robustness in explainable AI is the reliability, consistency, and resilience of explanations across tasks and environments. Robust explanations help stakeholders trust and rely on AI insights. This is especially important in high-stakes applications, where weak or unstable explanations can undermine decisions. Explainability varies by method and case. The material shows a recurring pattern. SHAP often provides more consistent feature attribution, but it may struggle with rare cases and large models. LIME gives quick local explanations, but similar inputs can receive different explanations. Rule-based models remain transparent, yet they may lack adaptability. Two major robustness challenges are highlighted. Adversarial attacks can manipulate explanations, causing SHAP or LIME to highlight misleading or irrelevant features. Complex, high-performing models create a second problem because deep neural networks are opaque, hard to scale, and difficult to explain consistently. Explaining models is hard. The recommended practices are practical. Select methods that fit the context, using post hoc explanations for complex black box models and intrinsic methods where high transparency is required. Balance accuracy and interpretability. Engage domain experts, and test explanations under different scenarios for consistency and reliability. 02, 03, 04, 05. For implementation, the material names LIME, SHAP, and LO5. LIME explains individual predictions through local surrogate models. SHAP provides global and local feature importance. LO5 offers feature importance and weights for linear and tree-based models, supporting practical evaluation across applications. One practical exercise uses the UCI Adult Income Dataset. The steps are to train a classification model, use LIME for an individual prediction, apply SHAP for feature importance, and compare results with LO5 permutation importance. The comparison highlights intuitive local insight, robust contributions, and speed trade-offs. AI explanations matter because trust, accountability, and regulation depend on understandable decisions. You have seen the main explanation approaches, their trade-offs, their robustness challenges, and the practical roles of LIME, SHAP, and LO5. The strongest choice depends on context, transparency needs, and how reliable the explanation must be.